All right, this is 2005, number 3. Excuse me. Student performs an experiment to measure the magnetic field along the axis of a long 100-turn solenoid PQ, as shown above. The end P of the solenoid is taped at the 0 centimeter mark, so it can't move. Solenoid can be stretched, so the position of end Q can be varied. The student then positions a Hall probe in the center of the solenoid to measure the magnetic field along its axis. She measures the field for a fixed current of 3 amps and various positions for the end of Q. The data she obtains is shown below. Complete the last column of the table by calculating the number of turns per meter. So turns per meter, we obviously have the stretch length right here. So turns per meter, we know it has 100 turns, right? It says that right here, 100 turns. So for the first one, I'm just going to do one example and then I'll plug in the rest. But 100 turns divided by 0.4, turn that into meters. 100 divided by 0.4 will give us 250. 100 divided by 0.5 will give us 200. 100 divided by 0.6 will give us 167. For some reason, if you check out the scoring guidelines, they're specific about the number of sig figs, right? These are all given in 3 sig figs. So here, the turns per meter, they want those to be in sig figs, correct sig figs. So if you put 4 sig figs, they took off. I'm assuming for like this one where you could have written 6.6666666666, that would be too much. 100 divided by 0.8, 125, and 100 divided by 1 is 100. I don't even have to plug that one in. So smart. Okay, so there are our turns per meter. Now we want to, on the axis below, plot the measured magnetic field versus N, draw a best fit line for the data points. So I have 9.7 and 250. So 250, 9.7 is probably like here. $207.7. 7.7 is like here. It's actually probably a little bit lower than that, but 167 and 6.8. 150, 60, 70, 80, 91. So 150, 67 is going to be in here. And I forgot what, 7.8? 6.8. All right. So 167 and 6.8 is going to be like here. Um, 125 and 4.9, 110, 25, and I keep forgetting 4.9, 4.9, 125, 10, 25, 4.9, like here, and 104. Oh, that's a nice one. 104. All right, draw a best fit line straight through the data points. This one I might actually have trouble with because I can't draw a straight line here. So maybe I can do shape to math and it'll let me draw a straight line. Did it turn it into a straight line? I don't think it did. Can I grab it? Stop. There we go. At least I can move it now, right? We want a couple above, a couple below. So that's not bad. I mean, you guys, if we had a meter, a ruler or something, I could do better, but that's not bad for a line of best fit. Cool. So there's my data points and my line of best fit. It looks like everything's pretty close, so I must not have messed up any of my data points. From the graph, obtain a value for mu, the magnetic permeability of a vacuum. So if we look through our equation sheet, the one equation that relates or that has mu and B and N in it is B, which it's the equation for a solenoid, so it's kind of our obvious choice here. But the magnetic field of a solenoid is equal to mu naught, which is what we're looking for, times N times I. So how do we get mu naught times N times I, right? How do we figure out mu naught here? Well, we have a graph, and if we look at what's measured in the graph, right? In the graph, we have B and N. So Y is B, X is N. So if we write this out, right, it would be B equals slope, right, because this is linear, times N plus y-intercept, right, which looks like it's heading towards 0. So if we ignore the y-intercept, right, we can relate these two equations, and the slope becomes what's left over, right? B, N. The slope becomes what's left over, which means the slope of our graph here is equal to mu naught times I. All right, where we're given in the very beginning that I is equal to 3 amps. So if I can figure out the slope of the line, right, so I come up here, I'll pick 2 points on my line, points that look kind of nice. So I'm going to pick this point and this point, right? So 2 points on the line, that'll give me, and then I just find the slope, which is rise over run, right? So rise, run. I still have ink to shape on. Stop, no more ink to shape. So we go from 5.5 up to 9.5. That is a rise of 4. And then we go from 140 to 240. That's a run of 100. So rise over run, we'll get 4 over 100. Oh, that's in times 10 to the 4th. So 4 times 10 to the negative 4th over 100 will give us our slope. 4 times 10 to the negative 4th over 100 will give us, what's that, 4 times 10 to the negative 6th. So the slope is 4 times 10 to the negative 6th. That's going to be equal to mu naught times 3. We divide that over, so 4 times 10 to the negative 6th divided by 3 gives us a mu naught value of 1.33 times 10 to the negative 6th. So there's my mu naught value that I calculated, right? Might not be perfect, but that's what I calculated. Oh, units. Let's see. We have if mu naught is equal to, well, we could just, where's my givens here? I just look up the units for mu naught instead of trying to remember them off the top of my head. Mu naught is Tesla meters per amp. Tesla meters per amp. There we go. All right, so there's my units for mu naught. And then we go ahead, we compare that. Now we'll have to actually calculate this part out to compare it. So percent error are calculated minus the actual absolute value over the actual times 100. 1.33 times 10 to the negative sixth minus 4 pi is 12 times 10. So we'll get minus 12.6 times 10 to the negative seventh divided by 12.6 times 10 to the negative seventh times 100. 1.33 times 10 to the negative sixth minus 1. I don't know why 4 pi. Times 10 to the negative seventh equals I guess that sounds about right. So we get 7.33 ish times 10 to the negative eighth divided by 1.2 or 12.6 times 10 to the negative seventh divided by 4 pi. I guess you could just keep it as 4 pi times 10 to the negative seventh the whole time. I don't know why I confused or converted it to a 12.6. That didn't make a whole lot of sense. Times 100. I got 5% error. I forgot the times 100 here. Times 100 equals 5.84%. I don't know if they're looking for a specific value. Like if you did really bad, do you get less credit there? What's it say? Their percent error was 0.35 or 3.5, which was a little bit better than mine, but whatever, screw them. So there is problem number 3 for you. All right. Let me stop this. If this little thing will come up, and I'll get you the next one.